In this video, I would like to discuss enhanced oil recovery. And my presentation would be along these lines. I would provide a background to enhanced oil recovery, discuss briefly technical screening guides for EOR. I'll go into the three major EOR processes, and then share some thoughts on the implementation of enhanced oil recovery projects. While primary and secondary recovery targets mobile oil in the reservoir, tertiary recovery or enhanced oil recovery targets immobile oil, and that's oil which cannot be produced due to capillary and viscous forces. Traditionally, primary, secondary, and tertiary recovery follow a natural progression of oil production from start to a point where it's no longer economical to produce from the hydrocarbon reservoir. The natural recovery processes that attempt to recover oil beyond secondary methods or what is left. Now, this view graph kind of summarizes the different oil recovery schemes. And then you would see it starts at the top with primary recovery for which natural flow and artificial lift is typically adopted. And then you have secondary recovery processes, which was discussed in an earlier video. And then you have enhanced oil recovery. Here you have thermal, gas injection, chemical recovery, and other methods, even though in this video I would stick to thermal, gas injection, and chemical methods, with microbial being discussed under chemical methods. It's worth noting that the term improved oil recovery refers to both secondary recovery and tertiary recovery methods. Now, this gives an overview of enhanced oil recovery projects operating since the 1970s. The green represents some thermal methods. While the one that kind of looks like a very dull yellow is for carbon dioxide enhanced oil recovery methods. And then you would see why you notice a decline in the chemical methods, which is the kind of the dirty blue. You would see an increase in the gas injection EOR methods. For thermal methods, it's kind of stabilized. If you had a spike, and then from the 90s, you started having a decline, and then had a slight a steady number of projects from the early 2000s. So the International Energy Agency estimated about 375 enhanced oil recovery projects. That's in 2018, which will produce slightly more than 2 million barrels per day. And as of 2018, when this survey was carried out, the production from EOR was broadly stable, contributing about 2% of global oil production. Here I have outlined the drivers and comparing them to the challenges in adopting enhanced oil recovery. As for the drivers, you see that due to maturing assets being developed using conventional methods, reserve replacement requires developing assets with typically immobile oil, which is quite difficult and expensive. And then recovery factors for many fields have been stuck in the mid 30% range. So there is significant oil in place which can be recovered using EOR methods. And with maturing EOR technologies, after pilot testing, a number of methods which were previously thought to be uneconomical have shown attractive economics. As regards challenges, implementing EOR is intimately tied to the price of oil and, of course, overall project economics. EOR is capital and resource intensive, and there's also long lead time for equipment, and for chemical methods, you also have high injectant cost. And of course, these aggravating projects cost also come along with fluctuations with the price of oil. And then the unit cost of EOR oil, that's oil recovered via EOR, is substantially higher than secondary and conventional oil, even though that's also a function of project scoping. And then there's the issue of the environmental footprint. So let's look at technical screening guides for EOR projects. The objective of the screening process is to decide which EOR method may be applicable in a reservoir and which methods are definitely not applicable. So the starting point is a set of basic properties that should be available for any reservoir. So screening criteria are based on physical principles associated with each method and economic assumptions. It's quite subjective, and there are minor variations from author to author on specific requirements. So typically you have conventional screening guides which entail comparing the average reservoir data for the reservoir in question with what you have in some lookup tables. A more thorough job could be done by considering available data like login data, repeat formation tester data, other sampling data, special core analysis, mineral studies, and PVT analysis. And then, of course, there's also advanced EOR screening using artificial intelligence techniques and some other analytical models which incorporate economic and cost modeling to a large extent. So in some instances, only one type of EOR technique is applicable for a specific field condition, but in many instances, more than one technique is applicable. The selection of the most appropriate process is facilitated by matching reservoir and fluid properties to the requirements necessary for individual EOR techniques. So in the next few slides, you see different conventional screening and lookup tables which have been developed. This is the US Department of Energy 1984 screening criteria. So you would see in the columns screening parameters, units, and then the different methods for chemical flooding, miscible flooding, and thermal recovery. So you see that different properties are listed, and then some guide to, for instance, if you're having your the oil gravity for your crude to be less than 25 API, you definitely would not be considering miscible flooding. Of course, you might need to think of thermal recovery or probably some alkaline, surfactant, polymer, chemical flooding method. And of course, there is, know that this is not absolute, but there are quick guides for you to decide, especially when you have a large pool of fields. You can just categorize them as those are for you can now select methods that are applicable or screen out methods which will definitely not work for your specific case. This is TABA screening criteria in 1997. So you see, in his case, the EOR methods are in the rows. API gravity range is given, viscosity, also composition of composition is given, and then the residual or saturation, preferred residual saturation is also stated, formation type, net thickness, and then of course the NC here refers to properties that are not critical, and then there's depth and there's temperature. This is more recent than the first two I've presented. This by Dixon et al. And then the SP paper of reference is quoted there. So here you just have the, so the first, that's row, column 2 to 4, miscible gas injection methods, column 5 to 7 or 5 to 8 thermal EOR methods, while the last two columns are chemical EOR methods. Now, the next three tables are tables extracted from petroleum engineering practice by Nemeka Ezekwe. And in his case, he had tables specific to the different methods. So for miscible gas injection, so you see that to the left, these are the major methods. Okay, this nitrogen flue gas, hydrocarbon gas, carbon dioxide, and then you see, so this just gives you an idea to the methods that could be applicable in to your own specific field case. And this is the same thing for a similar table for chemical flooding processes, and this for thermal flooding purposes. And you could always make reference to these tables later. And as I mentioned, you see, in this case, in contrast to the SP table, which which was shown at the beginning of the presentation, microbial enhanced recovery is listed here as part of chemical flooding processes. So let's go into the enhanced oil recovery processes. So EOR methods are classified by the main mechanism of oil displacement. They are really just three basic mechanisms for recovering oil from rock and other than by water alone. The methods are grouped according to those which, firstly, rely on a reduction of oil viscosity. Secondly, the extraction of oil with a solvent. And thirdly, alteration of capillary and viscous forces between oil injected fluid and the rock surface. So these are the three basic mechanisms which EOR methods exploit. So let's go into miscible gas injection to gas flooding. Remember that the conventional screening tables have been presented earlier. So a miscible gas displacement process is defined as a fluid displacement where there is no interface between the displacing fluid and the displaced fluid. So this contrasts to this is a clear contrast to immiscible displacement, especially for gas immiscible displacement. Gas injection, especially for carbon dioxide or carbon dioxide, is another popular EOR method, and it's applicable to light oil reservoirs in both carbonates and sandstones. It's popular for two main reasons. First, increased oil recovery through miscibility, and then it's attractive because you could also dispose greenhouse gases to improve the oil recovery. And there are several of these projects around the world. We saw that you're having rising number of gas injection projects, gas injection EOR projects with the years. Let's just go into some basic concepts. So miscibility has been mentioned. The concept of miscibility in a gas displacement process can be demonstrated with a ternary phase diagram. And so this is a ternary phase diagram for a methane, normal butane decaying system at 250 psi and 160 degrees Fahrenheit. So the two-phase region is within this envelope. This is the bubble point line. This is the plate point. It's actually the critical point. And then this is the dew point line. So within this envelope where you have these tie lines, this is the region of immiscibility. But outside the envelope, everything outside the envelope is the compositions are miscible. The relative size of the two-phase envelope in figure 6.1 or figure 6.2, as the case may be, depends on temperature and the pressure of the system. Increasing the pressure of the system at a constant temperature will shrink the two-phase envelope. So you see, if the pressure of this system is increased, for instance, from 2,500 psi to about 3,000, there's going to be a shrinking of this envelope to get smaller. This also means that at higher pressures, more compositions of the mixture are immiscible. This also means that at higher pressures, more compositions of the mixture are immiscible at 160 degrees Fahrenheit. I think the import of what is being, I think that should actually be miscible, not immiscible. At higher pressures, more compositions should be miscible at that temperature. For simplicity, a pseudo-ternary diagram could be, this could be represented by a pseudo-ternary diagram as shown in figure 6.2. So you see here at the vertices of this triangle, this is 100% methane, this is the C+7 fraction, and this is the C2s to C6. So there are two basic miscibility phenomena. So you have first contact miscibility and multiple contact miscibility. And for first contact miscibility, it occurs when the injected fluid is completely miscible with the reservoir fluid under the existing reservoir pressure and temperature. So under first contact miscibility, the injected fluid completely mixes with the reservoir fluid to create a transition fluid that miscibly displaces the reservoir fluid. First contact miscibility can be considered as an instantaneous process of complete mixing of the injected fluid with the reservoir fluid. The factors that determine first contact miscibility are reservoir temperature, pressure, composition of the injected fluid, and composition of the reservoir fluid. So you see the shaded portion here is the region of first contact miscibility, and while the shaded part is where, so remember that within this envelope, this is where you have this the immiscible region, and I guess your guess would be like mine, that this should be where multiple contact miscibility comes into place. So for multiple contact miscibility, this is achieved as a result of repeated contact between the reservoir and the injected fluid, and also fluids generated in situ by interactions between the two fluids. There are two main processes by which multiple contact miscibility is achieved. One is the vaporizing gas drive and the condensing gas drive. For the vaporizing gas drive, the composition of the injected fluid is progressively modified. The composition of the injected fluid is progressively modified by vaporizing the intermediate hydrocarbon components in the reservoir oil until there's a modified fluid, which leads to miscibility between the two systems. In contrast, for the condensing gas drive, intermediate hydrocarbon fractions in the injected fluid condense in the reservoir oil to generate the modified fluid, which becomes miscible with the injection fluid. And then there's a third process, which is a combined condensing and vaporizing gas drives. And this is quite applicable to CO2 EOR processes. The type of multiple contact miscibility process that is dominant in the displacement drive depends on the composition of the reservoir oil, composition of the injected fluid, pressure and temperature of the system. I just defined these two terms because they are quite critical. Minimum miscibility pressure. This is the minimum pressure at which multiple contact miscibility can be achieved in the reservoir for the fluid system. At pressures less than the minimum miscibility pressure, the displacement will be immiscible. So the minimum miscibility pressure is key to establishing miscibility. And of course, what you have there is defined as the minimum pressure at which the reservoir oil composition lies on the critical tie line extension for a specified fluid system. And this is when you are examining this phenomenon in the light of the ternary diagrams. For minimum miscibility enrichment, this describes the process of enriching the composition of the injection gas with intermediate hydrocarbons to achieve miscibility. So you could also look at these two in the light of the vaporizing gas drive and the condensing gas drive. Vaporizing gas process and the condensing gas process. So these are two related terms, but which both aim towards achieving miscibility. This isn't covered in this sensibly in this presentation. That's determination of minimum miscibility pressure, but it's still good to highlight that you have analytical techniques and experimental methods available for determining the minimum miscibility pressure. As regards analytical techniques, they are based on numerical computations, which could be further divided into empirical correlations or compositional simulations. And in the petroleum engineering practice, several empirical correlations are presented, which can be used to estimate the minimum miscibility pressure applicable to the test case. As for compositional simulations, equations of states are generally used to predict the minimum miscibility pressure or minimum miscibility enrichment, as the case may be. For experimental methods, the two common commonly used are the slim tube method and the rising bubble apparatus method, as I mentioned. It's not, I didn't go further on this in this presentation. So different types of gases can be used for miscible flooding, which include nitrogen, flue gases, and light hydrocarbons, and of course, carbon dioxide, as mentioned. Flue gases are generated from power plants, internal combustion engines, and they contain a mixture of nitrogen, carbon dioxide, and other gases with some trace amounts of sulfur dioxide and oxygen. So the minimum visibility pressure for flue gas injection is close to what you have for nitrogen. So in most texts, you will see nitrogen and flue gases grouped together when discussing miscible gas flooding. You need to note that due to the presence of carbon dioxide and sulfur dioxide, flue gases will be quite corrosive. The manner in which miscibility is achieved depends on the injection gas. So for nitrogen and flue gases, miscibility is achieved using the vaporizing gas drive mechanism, while for hydrocarbon gas and carbon dioxide, multiple contact miscibility is basically through the vaporizing gas drive, condensing gas drive, or combined gas drive mechanism, depending, of course, on the composition of the two, the reservoir fluid and then the injected fluid. As regards the nitrogen and flue gases, the economic appeal for their use stems from the fact that they cost lower than on a standard 1,000 cubic feet basis as compared to hydrocarbon gases or CO2, and they also have a lower compressibility. However, they are inferior to the other gases from an oil recovery point of view because nitrogen has a lower viscosity and it has poor solubility in oil. So a higher pressure is required to develop miscibility. And I had earlier mentioned the mechanism through which miscibility is achieved for these gas systems. And because it uses the vaporizing gas drive mechanism, nitrogen gas or flue gases are suitable for light oil reservoirs, are suitable for light oil reservoirs in deep formations. For hydrocarbon gases for miscible injection projects or miscible gas flooding, we have three different categories. The first category involves injecting liquefied petroleum gases such as propane and butane at pressures sufficiently high to achieve first contact miscibility. The second is injecting enriched gases, that's in the C2 to C6 range, to achieve multiple contact miscibility, predominantly using the condensing gas drive mechanism. And the third category is injection of lean gases, which are mostly methane, at high pressures to achieve multiple contact miscibility by vaporizing the light components in the oil. So in addition to the enhanced oil recovery due to miscible conditions, the injecting hydrocarbon gases improves oil recovery by swelling in the oil and reducing oil viscosity and physical displacement of the oil vapors. However, there's a downside to it. Application of hydrocarbon gas flooding is limited by poor sweep efficiencies due to potential for viscous fingering and the high economic value of hydrocarbon gases. CO2 EOR projects are the most popular of the miscible gas flooding processes.